A light-emitting diode, LED, is a semiconductor device that emits light when current flows through it. Electrons in the semiconductor recombine with electron holes, releasing energy in the form of photons. The color of the light, corresponding to the energy of the photons, is determined by the energy required for electrons to cross the band gap of the semiconductor. White light is obtained by using multiple semiconductors or a layer of light-emitting phosphor on the semiconductor device. Appearing as practical electronic components in 1962, the earliest LEDs emitted low-intensity infrared, IR, light. Infrared LEDs are used in remote control circuits, such as those used with a wide variety of consumer electronics. The first visible light LEDs were of low intensity and limited to red. Early LEDs were often used as indicator lamps, replacing small incandescent bulbs, and in 7-segment displays. Later developments produced LEDs available in visible, ultraviolet, UV, and infrared wavelengths with high, low, or intermediate light output, for instance, white LEDs suitable for room and outdoor lighting. LEDs have also given rise to new types of displays and sensors, while their high switching rates are useful in advanced communications technology with applications as diverse as aviation lighting, fairy lights, strip lights, automotive headlamps, advertising, general lighting, traffic signals, camera flashes, lighted wallpaper, horticultural grow lights, and medical devices. LEDs have many advantages over incandescent light sources, including lower power consumption, a longer lifetime, improved physical robustness, smaller sizes, and faster switching. In exchange for these generally favorable attributes, disadvantages of LEDs include electrical limitations to low voltage and generally to DC, not AC, power, the inability to provide steady illumination from a pulsing DC or an AC electrical supply source, and a lesser maximum operating temperature and storage temperature. LEDs are transducers of electricity into light. They operate in reverse of photodiodes, which convert light into electricity. In a light-emitting diode, the recombination of electrons and electron holes in a semiconductor produces light, be it infrared, visible, or UV, a process called electroluminescence. The wavelength of the light depends on the energy band gap of the semiconductors used. Since these materials have a high index of refraction, design features of the devices such as special optical coatings and die shape are required to efficiently emit light. Unlike a laser, the light emitted from an LED is neither spectrally coherent nor even highly monochromatic. Its spectrum is sufficiently narrow that it appears to the human eye as a pure, saturated, color. Also, unlike most lasers, its radiation is not spatially coherent, so it cannot approach the very high intensity characteristic of lasers. LEDs are made in different packages for different applications. A single or a few LED junctions may be packed in one miniature device for use as an indicator or pilot lamp. An LED array may include controlling circuits within the same package, which may range from a simple resistor, blinking or color changing control, or an addressable controller for RGB devices. Higher powered white emitting devices will be mounted on heat sinks and will be used for illumination. Alphanumeric displays in dot matrix or bar formats are widely available. Special packages permit connection of LEDs to optical fibers for high-speed data communication links. The current in an LED or other diodes rises exponentially with the applied voltage, see Shockley diode equation, so a small change in voltage can cause a large change in current. Current through the LED must be regulated by an external circuit such as a constant current source to prevent damage. Since most common power supplies are, nearly, constant voltage sources, LED fixtures must include a power converter, or at least a current limiting resistor. In some applications, the internal resistance of small batteries is sufficient to keep current within the LED rating. Some of LED's advantages. Efficiency: LEDs emit more lumens per watt than incandescent light bulbs. The efficiency of LED lighting fixtures is not affected by shape and size, unlike fluorescent light bulbs or tubes. Color: LEDs can emit light of an intended color without using any color filters as traditional lighting methods need. This is more efficient and can lower initial costs. Size: LEDs can be very small, smaller than 2mm2, and are easily attached to printed circuit boards. Switch on time: LEDs light up extremely quickly. A typical red indicator LED achieves full brightness in under a microsecond. LEDs used in communications devices can have even faster response times. Cycling: LEDs are ideal for uses subject to frequent on-off cycling, unlike incandescent and fluorescent lamps that fail faster when cycled often, or high-intensity discharge lamps, HID lamps, that require a long time to warm up to full output and to cool down before they can be lighted again if they are being restarted. Dimming: LEDs can very easily be dimmed either by pulse width modulation or lowering the forward current. This pulse width modulation is why LED lights, particularly headlights on cars, when viewed on camera or by some people, seem to flash or flicker. This is a type of stroboscopic effect. Cool light: in contrast to most light sources, LEDs radiate very little heat in the form of IR that can cause damage to sensitive objects or fabrics. Wasted energy is dispersed as heat through the base of the LED. Slow failure: LEDs mainly fail by dimming over time, rather than the abrupt failure of incandescent bulbs. Lifetime: LEDs can have a relatively long useful life. One report estimates 35,000 to 50,000 hours of useful life, though time to complete failure may be shorter or longer. Fluorescent tubes typically are rated at about 10,000 to 25,000 hours, depending partly on the conditions of use, and incandescent light bulbs at 1,000 to 2,000 hours. Several DOE demonstrations have shown that reduced maintenance costs from this extended lifetime, rather than energy savings, is the primary factor in determining the payback period for an LED product. Shock resistance: LEDs, being solid-state components, are difficult to damage with external shock, unlike fluorescent and incandescent bulbs, which are fragile. Focus: the solid package of the LED can be designed to focus its light. Incandescent and fluorescent sources often require an external reflector to collect light and direct it in a usable manner. For larger LED packages, total internal reflection, TIR, lenses are often used to the same effect. When large quantities of light are needed, many light sources such as LED chips are usually deployed, which are difficult to focus or collimate on the same target. Some of LED's disadvantages: temperature dependence: LED performance largely depends on the ambient temperature of the operating environment, or thermal management properties. Overdriving an LED in high ambient temperatures may result in overheating the LED package, eventually leading to device failure. An adequate heat sink is needed to maintain long life. This is especially important in automotive, medical, and military uses where devices must operate over a wide range of temperatures, and require low failure rates. Voltage sensitivity: LEDs must be supplied with a voltage above their threshold voltage and a current below their rating. Current and lifetime change greatly with a small change in applied voltage. They thus require a current-regulated supply, usually just a series resistor for indicator LEDs. Color rendition: most cool white LEDs have spectra that differ significantly from a black body radiator like the sun or an incandescent light. The spike at 460 nanometers and dip at 500 nanometers can make the color of objects appear differently under cool white LED illumination than sunlight or incandescent sources, due to metamerism, red surfaces being rendered particularly poorly by typical phosphor-based cool white LEDs. The same is true with green surfaces. The quality of color rendition of an LED is measured by the Color Rendering Index, CRI. Area light source: single LEDs do not approximate a point source of light giving a spherical light distribution, but rather a Lamarckian distribution. So, LEDs are difficult to apply to uses needing a spherical light field. Different fields of light can be manipulated by the application of different optics or lenses. LEDs cannot provide divergence below a few degrees. Light pollution: Because white LEDs emit more short wavelength light than sources such as high-pressure sodium vapor lamps, the increased blue and green sensitivity of scotopic vision means that white LEDs used in outdoor lighting cause substantially more sky glow. Efficiency droop: the efficiency of LEDs decreases as the electric current increases. Heating also increases with higher currents, which compromises LED lifetime. These effects put practical limits on the current through an LED in high-power applications. Impact on wildlife: LEDs are much more attractive to insects than sodium vapor lights, so much so that there has been speculative concern about the possibility of disruption to food webs. LED lighting near beaches, particularly intense blue and white colors, can disorient turtle hatchlings and make them wander inland instead. The use of turtle-safe lighting LEDs that emit only at narrow portions of the visible spectrum is encouraged by conservancy groups in order to reduce harm. Use in winter conditions: since they do not give off much heat in comparison to incandescent lights, LED lights used for traffic control can have snow obscuring them, leading to accidents. Thermal runaway: parallel strings of LEDs will not share current evenly due to the manufacturing tolerances in their forward voltage. Running two or more strings from a single current source may result in LED failure as the devices warm up. If forward voltage binning is not possible, a circuit is required to ensure even distribution of current between parallel strands. With the development of high-efficiency and high-power LEDs, it has become possible to use LEDs in lighting and illumination. To encourage the shift to LED lamps and other high-efficiency lighting, in 2008 the U.S. Department of Energy created the L Prize competition. The Philips Lighting North America LED bulb won the first competition on August 3, 2011, after successfully completing 18 months of intensive field lab and product testing. Efficient lighting is needed for sustainable architecture. As of 2011, some LED bulbs provide up to 150 lm/W and even inexpensive low-end models typically exceed 50 lm/W, so that a 6-watt LED could achieve the same results as a standard 40-watt incandescent bulb. The lower heat output of LEDs also reduces demand on air conditioning systems. Worldwide, LEDs are rapidly adopted to displace less effective sources such as incandescent lamps and CFLs and reduce electrical energy consumption and its associated emissions. Solar-powered LEDs are used as street lights and in architectural lighting. The mechanical robustness and long lifetime are used in automotive lighting on cars, motorcycles, and bicycle lights. LED street lights are employed on poles and in parking garages. In 2007, the Italian village of Torreco was the first place to convert its street lighting to LEDs. Cabin lighting on recent Airbus and Boeing jetliners uses LED lighting. LEDs are also being used in airport and heliport lighting. LED airport fixtures currently include medium-intensity runway lights, runway centerline lights, taxiway centerline and edge lights, guidance signs, and obstruction lighting. LEDs are also used as a light source for DLP projectors, and to backlight newer LCD television, referred to as LED TV, computer monitor, including laptop, and handheld device LCDs, succeeding older CCFL backlit LCDs although being superseded by OLED screens. RGB LEDs raise the color gamut by as much as 45%. Screens for TV and computer displays can be made thinner using LEDs for backlighting. LEDs are small, durable, and need little power, so they are used in handheld devices such as flashlights. LED strobe lights or camera flashes operate at a safe, low voltage, instead of the 250 plus volts commonly found in xenon flash lamp-based lighting. This is especially useful in cameras on mobile phones, where space is at a premium and bulky voltage-raising circuitry is undesirable. LEDs are used for infrared illumination in night vision uses including security cameras. A ring of LEDs around a video camera, aimed forward into a retroreflective background, allows chroma keying in video productions. LEDs are used in mining operations, as cap lamps to provide light for miners. Research has been done to improve LEDs for mining, to reduce glare and to increase illumination, reducing risk of injury to the miners. LEDs are increasingly finding uses in medical and educational applications, for example as mood enhancement. NASA has even sponsored research for the use of LEDs to promote health for astronauts. Light can be used to transmit data and analog signals. For example, lighting white LEDs can be used in systems assisting people to navigate enclosed spaces while searching necessary rooms or objects. Assistive listening devices in many theaters and similar spaces use arrays of infrared LEDs to send sound to listeners' receivers. Light-emitting diodes, as well as semiconductor lasers, are used to send data over many types of fiber optic cable, from digital audio over Toslink cables to the very high bandwidth fiber links that form the Internet backbone. For some time, computers were commonly equipped with IRDA interfaces, which allowed them to send and receive data to nearby machines via infrared. Because LEDs can cycle on and off millions of times per second, very high data bandwidth can be achieved. For that reason, visible light communication, VLC, has been proposed as an alternative to the increasingly competitive radio bandwidth. VLC operates in the visible part of the electromagnetic spectrum, so data can be transmitted without occupying the frequencies of radio communications. Machine vision systems often require bright and homogeneous illumination, so features of interest are easier to process. LEDs are often used. Barcode scanners are the most common example of machine vision applications, and many of those scanners use red LEDs instead of lasers. Optical computer mice use LEDs as a light source for the miniature camera within the mouse. LEDs are useful for machine vision because they provide a compact, reliable source of light. LED lamps can be turned on and off to suit the needs of the vision system, and the shape of the beam produced can be tailored to match the system's requirements. The light from LEDs can be modulated very quickly, so they are used extensively in optical fiber and free space optics communications. This includes remote controls, such as for television sets, where infrared LEDs are often used. Optoisolators use an LED combined with a photodiode or phototransistor to provide a signal path with electrical isolation between two circuits. This is especially useful in medical equipment where the signals from a low-voltage sensor circuit, usually battery-powered, in contact with a living organism must be electrically isolated from any possible electrical failure in a recording or monitoring device operating at potentially dangerous voltages. An optoisolator also lets information be transferred between circuits that do not share a common ground potential. Thank you for watching this video.